Welcome to the third segment of multiple reaction system under the head of polymer reaction engineering. Now let's have a look about what we studied previously. We had a discussion about the qualitative treatment of two reactants in parallel reaction system. Now we discussed about the two reactants, both are reacting in a parallel reaction profile. Then we performed the quantitative treatment of product distribution and a reactor size in parallel reaction system. We discussed about the qualitative analysis of a series reaction system. Now in this particular lecture, we are going to discuss the quantitative analysis of a series reaction in PFR and batch reactors both. We will perform the quantitative treatment methodology of a mixed flow reactor. We will discuss about the first order followed by zero order reaction. We will have a discussion about the zero order followed by the first order reaction. So let's have a look about the quantitative analysis of a series reaction in PFR or batch reaction. Now as you recall that we had a discussion about the series reaction system where we were having X is converted into Y is converted into Z with the independent rate constants as we are representing over here. Now this if we go for the elaborative manner, then we can say that the X is decomposed into the desired product Y and further it is decomposed into the undesired product Z. The most important factor here is the contact time and the space time for batch and flow reactor respectively. Now if the desired product produced with a lower kinetic order for the undesired reaction, then it is difficult to produce the desired product Y. So the first reaction's order should be higher than the second one for a higher yield of Y. Now another factor is the contact time in a batch reactor, the space time in the flow reactor. This should not be longer as the desired product to decompose further into the undesired product. So you should not give more time to grab this particular aspect. Now this particular thing should kept into mind while we design the reaction protocol, while we design the size of the reactor. Now here we have to maximize the intermediate product Y because this is the desired one. We should not promote the formation of undesired one. So that is why you need to adjust the space time and the contact time both accordingly. Now when we talk about the rate equation for the decomposition of a reactant which we discussed in this slide. Now here the rate equation for the decomposition of a reactant X can be termed as Rx is equal to dCx dt is equal to minus kycx. Now this may be termed as equation number 1. Then you can say that this is Rx. Similarly, if I write the rate equation for intermediate, that is Y, then it can be represented as Ry is equal to dCy upon dt, that is the concentration of Y. Now since it is constantly being formed as well as constantly being consumed, then we can write that as kycx minus kzcy, that is equation number 2, and we can write this kz. Now since here we experience the formation of undesired product Z, then the rate equation for the undesired product can be written as Rz is equal to C dCz upon dt, this is equal to kz cy, and you can say that this equation is equation number 3. Now sometimes we need to find out the concentration of X at any time. So if we use the space time in place of time, in the batch reactor performance equation, then these equations can be used for plug flow reactor too. So, if at the initial concentration or initial condition of the concentration of the reactant X is Cx at time Cx naught at time t is equal to 0 and Cx at time t is equal to t. So, if we rearrange and integrate the equation which we discussed in this slide, then we may have Cx naught Cx dCx upon Cx, this is 0 to t minus ky dt, or it is represented as Cx is equal to Cx naught e to the power minus ky t, or Cx upon Cx naught is equal to e to the power minus ky t. Let us say that this is equation number 4. Now, if we talk about the balance of Cy, that is remember this is the intermediate. So, in we can rearrange this equation number 2 which we represented over here. If we rearrange this equation, then we may have dCy dt plus kz Cy, and that is kz Cx naught e to the power minus ky t. This can be represented as equation number 5. Now, if we compare the equation 5 with a linear differential equation and solved it with the integration factor method, then the linear differential equation can be represented as dy over dx plus px y is equal to phi x, that is equation number 6. Now, integration factor you can write if can be written as e to the power px dx. So, integration factor for equation number 5, if we try to write that, that may become integration factor e to the power k z t. Now, if we multiply this integration factor on both sides of the equation 5, then we may have dCy dt e to the power kz t plus kz Cy e to the power kz t is equal to kz Cx naught e to the power minus ky t e to the power k z t. Now, that is d Cy e k z t upon dt, this is equal to k z Cx naught e to the power minus ky t e to the power k z t. You can write this as equation number 7. Now, upon integrating this equation with the initial moles of y with respect to that at time t is equal to 0, Cy will be 0 at time t is equal to 0, and Cy is equal to Cy at time t is equal to t. And then we need to find the value of concentration of y. So, we may have this 0 to Cy d Cy e to the power k z t is equal to 0 to t k z Cx naught e to the power minus ky t e to the power k z t dt. You may say that this is equation number 8. This can be rearranged and can be written as Cy is equal to ky Cx naught upon kz minus ky into e to the power minus ky t minus e to the power k z t. Now, you can write it as equation number 9. Now, if sometimes we are always looking for the optimum value. Now, the optimum value, when we talk about the optimum value, the concentration of intermediate reaches at maximum in a certain point within the reactor. So, to find out the optimum parameters or perimeter, we have to differentiate the equation number 9 which we discussed with respect to time and put equal to the 0. So, in that case we can write this as dcy upon dt is equal to 0, and this is kyc x naught upon kz minus ky minus ky e to the power minus kyt plus kz e to the power minus this kzt, not this is not minus t. Now, this may be termed as equation number 10. Now, if we solve for t for tau optimum value, in that case the tau optimum, that is 1 upon ky minus kz ln ky upon kz, that may become the equation number 11. Now, if we put the value of this tau optimum to the equation in the previous equation 10, we have the maximum value of Cy. So, the amount of Cy formation is higher in case of the ratio of specific rate constant Ky and Kz is greater than 1, and the lower when the ratio is less than 1. So, when we try to write the conversion of x at the maximum Cy, so we can write the mathematical equation x optimum, that is equal to Cx naught minus Cx upon Cx naught, that is equal to 1 minus e to the power minus kyt optimum, and this you can represent as equation number 12. Now, if we substitute the value of tau optimum in this particular equation, we may have this x optimum, that is equal to 1 minus ky upon kz to the power ky upon ky minus kz. That is the equation number 13. Now, sometimes you may be interested to find out the value of Z with respect to the concentration, and that is sometimes referred as Cz. So, the value of Cz, this can be obtained from the overall balance of moles consumed and remaining during the reaction of time. Now, you can put the value of all in terms of right hand side, we obtain the value of Cz at any instance. So, let us put in the mathematical form, that is Cz is equal to Cx naught minus Cx minus Cy. This is quite obvious, that is the concentration of x at start, then concentration after time t, and then concentration of y, that is the intermediate after time t. So, we can put this as equation number 14. Now, if we try to plot this thing and we represent with respect to the ky tau and xx, you can see the behavior of your flow or reactor, etc. Then you will find different things that is related to C upon Cx naught, and you see that at start the concentration and conversion graph of PFR with a different value of Kz and Ky in series reaction system. So, you can see that here you can have the values of this one, like Kz upon Ky is equal to 0 and Kz upon Ky is equal to 1. Now, let us have a look about the quantitative treatment for mixed flow reactor. Now, here we have discussed about this the mixed flow reactor. Now, here you are having a reactant which is coming into this reactor system having the concentration C. This reactor is having the volume V, and it is the stirred type of reactor or the mixing type of a reactor. Now again we are coming back to our original equation for this one, that is the equation concentration of X decomposes into the intermediate Y, and further Y is decomposed in the undesired product Z, which is as per the requirement it need to be minimized in due course of time. So, in that case if the series of above reaction takes place in a mixed flow reactor, initially the concentration of Y and Z are not present in the reactor. So, initially only X is present, the concentration of X is present. So, in other words we can say if we perform the steady state material balance for the component X, that is the input of X is equal to output of X plus disappearance of X by reaction. So, we can write the steady state material balance equation for X, and that is Fx naught is equal to Fx plus, since it is being consumed in due course of time or disappearing in due course of time, that is why we are putting minus sign over here, and this is the equation number 15. Now, if we put this value into the previous equation, then we may have nu nu Cx naught is equal to nu Cx plus Ky Cxv. Now, this is equation number 16. So, here nu is equal to Fx naught upon Cx naught is equal to Fx upon Cx, and minus Rx is equal to Ky Cx, and if we put this all values in the previous equation and rearrange this, then we may have this V upon nu is equal to tau T, this is equal to tau M. This is my next equation. Now, here as I evident that volume is V, volume of the reacting fluid, it is represented as meter cube. Then nu is the volumetric flow rate of reacting fluid. This is the units are always represented as the second inverse. Then tau m is the space time of the mixed flow reactor. Then T is the contact time of the reacting fluid, Cx is the concentration of the reactant after time t, and Cx naught is the initial reactant concentration, and Ky is the specific rate constant, and N is the order of the reaction. Now, if we rearrange the things of equation 17 and 18 in the previous slides which we discussed, then we may have this equation, this Cx upon Cx naught is equal to 1 upon 1 plus Ky tau m, and material balance equation. If we try to write the material balance for component Y, we may have nu Cy naught is equal to Cy nu Cy plus R, because R the sign of this Ry is putting positive because it is being consumed in due course of time. Now, at initially the concentration of intermediate Y is 0, because at time t is equal to 0, and when reaction proceeds then it acquires some values. So, in that case we can put like this: 0 is equal to nu Cy plus minus Ky Cx plus Kz Cy V. Now, if we rearrange this equation, that is referred as equation number 20. Now, if we rearrange this equation, we may have Cy upon Cx naught is equal to Ky tau m upon 1 plus Ky tau m into 1 plus Kz tau m. That you can write as equation number 21. So, by this way we can put all these equations in things. Now, if we try to calculate the value of Cz, Now we can write this thing like Cz is equal to Cx naught minus Cx minus Cy. Now it is quite obvious because we have already initiated this thing, that this is the initial concentration of X, then over the period of time the concentration of X becomes Cx, and then during this course of time the Cy is formed and it is further decomposing. That is why we are putting negative sign over here. Now in putting the values in this, let us say this is equation number 22. Now if we put the value of values in equation 22 and we solve, we can have the following relations like Cz upon Cx naught is equal to Ky Kz tau m square upon 1 plus Ky tau m into 1 plus Kz tau m. Now this you can term as equation number 23. Now for optimum value of space time and for the maximum intermediate concentration, this can be calculated by the differentiating this equation 21 previous equation with respect to tau m, and put you can put it to the 0. Then in that case this maximum intermediate equation may become like dCy upon d tau m, that is equal to 0. So you can say that this is equation number 24. Now if we simplify all these equations, we can find tau m optimum. Now this tau m optimum that can be represented as 1 upon square root of Ky Kz, that you can say the equation number 25. Now if put the corresponding values of Cy maximum, this can be calculated by putting the equation 25, this equation, in equation the previous equation where we find it out tau maximum tau m optimum, and if we rearrange all those things, then we may get this Cy maximum upon Cx naught, that is equal to 1 upon 1 plus Kz Ky to the power half. Now this you can term as equation number 26. Now you can easily plot these concentration and conversion graph for mixed flow reactant with the different values of Kz over Ky in series reaction system, and you may see that these are the standard graphs which we have requested from Levin-Spiel. Now if we take about these figures for series reaction system, then it shows the general time concentration behavior and actual progress of reaction. Now if we compare these figures for plug flow reactor and the mixed flow reactor, when Ky is equal to Kz, the plug flow reactor requires a smaller time than the mixed flow reactor to achieve the maximum concentration of Y. For any reaction, maximum concentration of Y can be obtained in the PFR, which is always higher than the maximum Cy obtained in mixed flow reactor. So these type of plots are most important for the kinetic study because they allow for the determination of Kz over Ky by matching the experimental point or validating those points within the one of two curves given in each type of a reactor, like either MFR or PFR in this thing. Now if we talk about the first order followed by the zero order reaction, that is quite evident in different type, because people may say that we are discussing these two reactions. There are two reactions indeed. One is that X is converting into Y, and the second one is that Y is converting into Z, irrespective that whether anyone is the desired and second one is the undesired one. So these are two reactions, and sometimes you may experience that the order of both the reactions are different. Like here we are going to discuss this thing, that first order followed by the 0th order. Here you are having this first order reaction, and here you are having this 0th order reaction. Then we try to find out, and we try to write the rate equation for the decomposition of a reactant. Now, if plug or batch reactor used for the completion of the reaction, in that case Rx is equal to dCx upon dt minus kycx. That you may say that equation number 1. And if we write the rate equation for the intermediate, then it may be Ry is equal to dCy upon dt, that is kycx minus kz. That is equation this was my equation number 1, and this is, if we take into the sequence, then it may become the equation number 27. So, the rate equation for undesired product, again it can be write down like this: Rz is equal to dCz upon dt is equal to kz. Now, you can write that equation number 28. Now, as initially the Cx naught is equal to Cz naught is equal to 0. So, rearranging and integrating this equation number 1 which we discussed, and this equation number 27, then in that case Cx upon Cx naught will become e to the power minus kyt. That you can say that equation number 29. Now, for intermediate, you can write Cy upon Cx naught is equal to 1 minus e to the power minus kyt minus kz upon Cx naught t. That you can say that is equation number 29. Now, sometimes it is quite obvious to write the equation for undesired product. So, for undesired product, you may write Cz is equal to Cx minus Cx naught minus Cx minus Cy. This equation is we have already discussed. So, if we differentiate these equation, and for the maximum concentration of the intermediate, because we are always claiming that my intermediate product is my desired product, and optimum time required for the maximum intermediate, this can be calculated by differentiating this equation which we discussed previously with respect to t and equal to and set equal to 0. Then in that case dCy upon d tau m, that is equal to 0, that you may say different set of equation. Now, if we solve this one, then we may have Ty optimum, that is equal to 1 upon ky ln 1 upon k, sorry, and where k is equal to kz upon Cx naught upon ky. Now, for maximum value of intermediate product, put the value of t tau y optimum in the above equation. This is the equation number 30 which we discussed previously. So, we may find the value of Cy maximum upon Cx naught, that is equal to 1 minus k 1 minus ln k. So, these are this is the desired equation which we are looking for. Now, if we plot the product distribution for first order followed by the 0th order, you can see here we have plot this TCR maximum, and this is the concentration profile. You can see that initially we are having this with the help of this equation 33, that CR maximum, and if you follow this previous equation 29, then you see that this curve is approaching to the minimum value. Now, sometimes in the other aspect or other things, that is that sometimes you may experience this thing, that 0 order followed by the first order. So here you see that this is the 0th order and this one is the first order. So the rate of reaction of reactant X, this can be put forward like this: Rx is equal to C dCx upon dt is equal to minus ky. And similarly, if we try to solve it, then it can become the Cx upon Cx naught is equal to 1 minus ky t upon Cx naught. Now for intermediate product y, if we try to write this, then Ry is equal to dcy upon dt, that is equal to ky minus kzcy, and this can be represented as dcy upon dt plus kzcy is equal to ky. Now, if we see that the rate of reaction of undesired product, it is quite obvious because we have to follow this series, then it can be put forward as Rz is equal to dCz over dt, then kzcy. Now, if we integrate this equation and found the integration factor, then if integration factor can be written as e to the power kzt. Now, if we multiply both the side with the integration factor in the previous equation, then we may have this cy is equal to ky kz into 1 minus e to the power minus kzt. Now, if we talk about the undesired product profile, you are always having this particular equation with you, that is Cz is equal to Cx naught minus Cx minus Cy. Now, if we differentiate this equation, the previous equation, then with respect to t and set or put forward equal to 0, then it may become this equation we are talking about, this Cy is equal to ky upon kz 1 minus e to the power kzt. Now, if we differentiate this equation with respect to t and put equal to the 0, then dcy upon dt is equal to 0. Now, if we solve this particular equation, then we may have tau optimum is equal to Cx naught upon ky. So, if we put all the values in this equation, we may have Cy maximum, that is equal to 1 minus e to the power minus k upon k, where k is equal to kz upon ky upon Cx naught. So, this is my final equation which I am looking for. Now, if we try to plot this thing with respect to the time and concentration, so you can see that we are obtaining a product distribution for 0 order reaction. Now, you see that with the help of a previous equation which we developed, you can find these two curves which are quite evident that what kind of a different product profiling you may have in this type of a reaction, where 0 order is followed by the first order reaction. Now, in this particular chapter, we have discussed about the different configuration. A special emphasis was given to the various reaction sequences, 0 order followed by first order and then first order followed by the 0th order. And again, for your convenience, we have enlisted a couple of references for further reading. Thank you very much.